Welcome back, traveler of the cosmos. Tonight, we're venturing into one of the strangest, most terrifying, and yet most beautiful mysteries the universe has ever given us. Black holes. They are monsters of gravity, destroyers of worlds, engines of paradox, and maybe just maybe doorways to something far beyond what we can imagine. Some people think of them as cosmic trash compactors, crushing everything into oblivion. Others dream of them as portals, shortcuts through space and time, maybe even gateways to other universes. Whatever they are, one thing is certain: black holes are not just objects in space. They are questions made real, and the deeper we look into them, the stranger the questions become. But before we fall into one, let's make ourselves comfortable. This isn't going to be a rushed lecture with equations flashing by. This is a journey. You don't need to remember every detail. You don't need to keep up with the math. Just listen, relax, and let the words paint the picture. Some of it may feel familiar, some of it may sound impossible, and some of it may feel like science fiction. That's okay. Black holes are where science and imagination already overlap. Of course, if you're joining me here for the first time, consider pressing that subscribe button so you don't miss the next cosmic adventure. And if you're already part of this little community, welcome back. Let me know in the comments where you're listening from: your couch, your bed, your night shift, or maybe a quiet walk under the stars. It's always a joy to know that in a universe this vast, we're sharing this moment together. So, black holes. Where do we start? Maybe with the simplest idea: gravity. You know it well. It keeps your feet on the ground, pulls the moon around the Earth, and the Earth around the sun. But gravity isn't just a force, it's geometry. Einstein taught us that mass bends space and time itself. The more massive the object, the more it bends. The sun bends space-time enough to hold Earth in orbit. A neutron star bends it so steeply that light itself curves around. And a black hole bends space-time so extremely that the curve becomes a cliff. Cross the edge, and there's no climbing back. That edge has a name: the event horizon. From far away, a black hole looks like a sphere of darkness, outlined maybe by glowing gas and shredded stars. But the event horizon is not a physical surface. It's a boundary, a one-way door. Once you pass it, not even light can escape. From the outside, it looks like the ultimate eraser. Whatever falls in is gone forever, leaving behind only the echo of its gravity. But from the inside, well, that's where things get interesting. Imagine you're falling toward a black hole. Don't worry, you're safe in thought. From your perspective, nothing unusual happens as you cross the event horizon. The laws of physics still apply. Your watch still ticks. Your heart still beats. But to someone watching from far away, it's a different story. They see you slow down as you approach the horizon. Your movements drag. Your signals stretch into longer and longer wavelengths, turning redder and fainter. To them, you never cross. You just freeze, fading away, as if time itself has stopped for you. That's one of the first paradoxes of black holes. Two observers, two realities, both correct in their own frames. But what happens after you cross? That's where the math grows dark. At the center of the black hole, hidden behind the horizon, lies the singularity. A pointer, more accurately, a region where density becomes infinite. Space-time curves infinitely, and our equations collapse. General relativity predicts it, but it cannot describe it. And that's unsettling. It's like a warning sign. Here be dragons. The singularity is not just a place, it's the edge of knowledge itself. Some physicists think singularities may not exist in reality. That quantum physics will smooth them out somehow. Others think they're very real, and that they may connect to something else, other universes, other dimensions, maybe even the birth of new Big Bangs. In fact, there's a provocative idea that every black hole might be a seed of a new universe, budding off from ours. If that's true, then maybe our own universe was born inside someone else's black hole already. You see how black holes refuse to stay in the box of ordinary objects. They are paradox machines, forcing us to ask questions we can't answer yet, and the questions only multiply. Take information, for example. In physics, information is sacred. It's the record of how particles are arranged, their states, their properties. The laws of physics say information can never be destroyed. It can change form, scatter, scramble, but never vanish. Yet black holes seem to defy that. Throw a book into a fire, and yes, the words are gone to but in principle. The smoke and ash still contain the information. Throw a book into a black hole though, and once it crosses the horizon, it's gone. No light, no signals, no retrieval. From the outside, it looks like the information has been erased. That's the infamous black hole information paradox. Stephen Hawking made it even stranger. He showed that black holes are not completely black. They radiate faintly, due to quantum effects at the horizon. This Hawking radiation means black holes can slowly evaporate, losing mass, shrinking, and eventually disappearing. But if they vanish, where does the information go? Does it evaporate too, violating the sacred rule? Or does it somehow leak out in scrambled form? Or does it get stored on the horizon itself, as some physicists now suspect, like a cosmic hologram? These are not small questions. They cut to the heart of physics, to whether our universe is predictable or not. And if that wasn't enough, black holes also flirt with the idea of time travel. Some solutions to Einstein's equations suggest that inside rotating black holes, so-called Kerr black holes, there might be paths, closed time-like curves, that loop back in time. Wormholes hidden within tunnels to other places or even other eras. In practice, these are unstable, likely destroyed by the very slightest disturbance. But the fact that they appear in the math at all is enough to set imaginations racing. Could black holes be natural time machines? Could falling into one mean not the end, but the beginning of another journey? But let's not get ahead of ourselves. For tonight, we're only beginning to trace the outlines of these cosmic mysteries. Think of black holes not as answers, but as questions painted on the canvas of the universe in the darkest ink. What happens at the singularity? Where does information go? Do event horizons hide portals? Are they endings or beginnings? Let's pause here. It's easy to feel overwhelmed by the strangeness, as if the ground beneath you has dissolved. But remember, black holes aren't just theory. They're real. We've seen the evidence. Stars orbiting invisible companions, matter swirling into darkness. Even recently, an actual image of a black hole's shadow, a glowing ring of light bent by gravity around the abyss. These monsters are not fantasies. They are out there, shaping galaxies, colliding, roaring in gravitational waves that ripple through space itself. So tonight, as you close your eyes or let your mind drift, hold on to this. Black holes are not just holes in space. They are holes in our understanding. And by studying them, we may not just learn about gravity, we may glimpse the deepest secrets of the universe. Next time, we'll fall deeper. We'll explore the strange ways black holes form, from collapsing stars to collisions of giants, and the violence that lights up the universe in their birth cries. But for now, rest with this thought. Somewhere out there, in the darkness, a star has died, a horizon has formed, and a new mystery waits at the edge of time. When we first hear the phrase black hole, it's tempting to imagine them as exotic, rare things. Maybe one or two hidden somewhere out there in the galaxy, far removed from us. But the truth is more startling. Black holes are everywhere. Our Milky Way alone may contain millions of them, scattered invisibly among the stars. To understand how they're born, we need to go back to the lives of stars themselves, because black holes are not foreign intruders. They are the corpses of stars. A star begins as a cloud of gas, mostly hydrogen. Gravity pulls the gas inward until the pressure in the core grows so intense that hydrogen atoms fuse into helium, releasing energy. That energy is what makes stars shine. It also provides the outward pressure that balances the inward pull of gravity. For billions of years, this delicate balance holds. The star lives its luminous life, burning, glowing, sending light across the cosmos, but eventually, fuel runs out. Small stars, like our Sun, end quietly, shedding their outer layers into beautiful planetary nebulae, leaving behind dense white dwarfs. Larger stars die more violently. When a star, many times the mass of the Sun, exhausts its fuel, gravity wins. The core collapses in a fraction of a second. The outer layers crash inward, then rebound in a titanic explosion, a supernova. For a brief time, a supernova can outshine an entire galaxy. The death of a star is one of the brightest events in the universe. And yet, in that brightness, something darker is born. If the collapsing core is heavy enough, even neutron pressure, the force that holds the densest matter, we know cannot resist gravity. The core keeps falling, compressing, until it crosses the point of no return. A black hole is born. A horizon forms. From that moment, the star's heart has been transformed into an abyss. The numbers are almost impossible to grasp. Imagine the sun collapsing into a black hole. All its mass, 330,000 times Earth's, crushed into a sphere about 6 kilometers wide. That's smaller than many cities. The Earth would keep orbiting normally because the black hole's gravity at Earth's distance would be the same as the sun's, but the sun itself would be gone, replaced by a silent shadow. That's what black holes are: mass without a surface, gravity without a face. But stellar collapse isn't the only way black holes form. When two neutron stars collide, they can merge into a black hole, releasing a flood of gravitational waves and a burst of gamma rays so bright it can be seen across billions of light. Sometimes, supermassive black holes at the centers of galaxies may be born from smaller ones merging and feeding, growing until they outweigh millions or billions of suns. In fact, every galaxy we know seems to have a supermassive black hole at its core, including ours. Sagittarius A*, a monster 1,000,000 times the mass of the Sun, lurks at the heart of the Milky Way, hidden behind clouds of dust but revealed by the stars that whirl around it like fireflies caught in its grip. How do we know these things are real? After all, black holes are invisible. They emit no light. They cannot be seen directly. For decades, they remained speculative, more mathematical ghosts than physical entities. Even Einstein, whose equations predicted them, was skeptical they could exist in reality. So what changed? The answer is that while black holes themselves are dark, their effects are not. Imagine a black hole with a companion star. Gas from the star spills into the black hole's gravity well, swirling around in a disk before falling in. That disk heats to millions of degrees, glowing with X-rays that telescopes can detect. By observing such X-ray binaries, astronomers have identified dozens of black hole candidates in our galaxy. Or consider stars orbiting something invisible. In the 1990s and 2000s, astronomers tracked stars near the center of the Milky Way, watching them complete dizzying orbits around nothing. The only explanation was an unseen mass, 4 million suns crammed into a tiny space. A supermassive black hole. The precision of those observations was astonishing. We weren't just theorizing anymore. We were watching stars dance around the darkness. And then, in 2019, came the image. The Event Horizon Telescope, a global network of radio telescopes linked together, captured the shadow of a black hole in the galaxy M87, a glowing ring of light bent around darkness, exactly as predicted. For the first time, we didn't just infer black holes. We saw one. The image stunned the world. It was blurry, imperfect, but it was history. A photograph of the unseen. Proof that these monsters weren't just math, they were real, and we could look them in the eye. But the story doesn't end there. In 2015, the LIGO Observatory made another breakthrough. It detected ripples in space-time gravitational waves from two black holes colliding over 1 billion light-years away. The signal lasted less than a second, a faint chirp in the detectors. But it confirmed Einstein's prediction and opened a new way of seeing the universe. Since then, dozens of black hole mergers have been detected, each one a cosmic cataclysm sending vibrations across space-time itself. We are no longer blind to black holes. We are listening to them sing. All of this paints black holes not as exotic oddities, but as fundamental actors in the universe. They are born in stellar deaths. They grow by feeding. They collide and merge. They anchor galaxies. They shape the cosmos at every scale. And yet, for all that, they remain paradoxical. They are both destroyers and creators. They erase and reveal. They are boundaries in space, but also boundaries in knowledge. And here's the strangest thought of all. Black holes may not be rare exceptions. They may be essential. Without them, galaxies might never have formed. Stars might never have gathered, planets and life might never have appeared. The very fact that we are here may depend on these cosmic monsters. In trying to understand them, we are not just chasing curiosities, we are chasing the story of our own existence. Still, the questions deepen. If black holes are so common, if they shape galaxies and maybe even universes, then what lies at their hearts? Are singularities real, or does quantum physics change the picture? Is the information we throw in really lost, or is it stored in ways we don't yet grasp? Could event horizons be holograms, encoding the universe in ways we've only begun to imagine? These are the mysteries we'll face next. But let's not rush. For now, picture it. Somewhere, right now, a massive star has just collapsed. Its core has crossed the line, its light has gone out, and in its place, a black hole has been born. Silent, invisible, waiting, and maybe hiding something more than destruction. Next time, we'll step closer to that question. We'll explore what might lie beyond the horizon. Wormholes, time loops, paradoxes. Are black holes, portals, or prisons? And if they are doorways, where do they lead? For now though, let yourself drift with this thought. The night sky is not just filled with stars. It is filled with ghosts. And those ghosts are what? Imagine standing at the edge of an event horizon. You can't touch it. You can't see it directly. But you know it's there, the ultimate boundary. A place where the rules of escape change forever. Step across, and no matter how fast you move, no matter what engines or wings you strap to your back, you will not get out. Space itself flows inward faster than light. From the outside, it looks like you've fallen into darkness. From the inside, it feels like nothing has changed at all, at least at first. The strangest paradox of black holes begins right here. At this invisible doorway. To an observer far away, nothing ever crosses the horizon. You could throw a spaceship, a planet, even an entire star at a black hole. And from their perspective, it would freeze at the edge. Its signals stretched thinner and redder until they fade into invisibility. From their view, the horizon is an impenetrable wall. Yet for the falling traveler, time continues. They cross without noticing, slipping silently past the line into a region cut off from the rest of the universe. Both realities are true, depending on where you stand. Two perspectives, one universe, each obeying the laws of physics, yet describing completely different outcomes. Cross the horizon, and the path inward is unavoidable. Every possible route through spacetime curves toward the singularity, the hidden heart of the black hole. There is no orbit, no escape trajectory. The singularity pulls all paths inward like a drain pulling water. And the closer you get, the stranger things become. Tides of gravity stretch you one way and compress you another. For stellar mass black holes, these forces grow so extreme that they would tear apart even the most solid matter. A process called spaghetti. Your body would be stretched thinner than thread, atom by atom, until you were drawn into the singularity's point of no return. But what is that singularity, really? Here's where physics trembles. General relativity predicts it as a point of infinite density, infinite curvature, infinite everything. But infinities in physics usually mean we've hit the limit of our understanding. They're like warning lights flashing, the math has broken down. That's why so many physicists suspect that quantum mechanics, the physics of the very small, must come to the rescue. Somewhere inside the black hole, relativity and quantum theory collide, and neither works properly alone. Until we have a theory of quantum gravity, the true nature of singularities remains hidden from us. Some ideas suggest that singularities may not be points at all, but regions where spacetime folds into strange shapes. Wormholes, for example. In certain mathematical solutions, the singularity isn't a dead end, but a bridge, a tunnel that leads somewhere else, another place in space, another time, maybe even another universe. A rotating black hole, known as a Kerr black hole, has such solutions. Instead of collapsing to a point, its equations allow for a ring-shaped singularity that might, in principle, be traversed. Inside, paths exist that loop backward in time, creating closed time-like curves. The math whispers of time travel, of shortcuts across the cosmos. But there's a catch. These solutions are fragile. The slightest disturbance, like a spaceship trying to pass through, would cause them to collapse. Radiation, quantum fluctuations, even the smallest ripple in spacetime would likely destroy the wormhole instantly. So, while the math is tantalizing, the physics may be less forgiving. Still, the possibility hangs there. Black holes as natural portals, cosmic stargates hidden in the fabric of the universe. Even stranger are white holes, hypothetical opposites of black holes. If a black hole swallows everything and lets nothing escape, a white hole would do the reverse. Nothing could enter, and everything inside would be expelled. Some equations link black holes and white holes together, forming wormholes through spacetime. We've never observed a white hole, but if they exist, they could be the other side of black holes, the exit door to somewhere else. Imagine falling into a black hole here, only to be ejected in another region of the universe or another universe altogether. Of course, all of this is speculation. No one knows what truly lies inside. It could be baby universes budding off like cosmic offspring. It could be that the singularity never forms, replaced instead by some exotic quantum structure we don't yet understand. Or, it could be exactly what relativity predicts, a point of infinite density, an inescapable dead end where the universe itself says, no further. And then there are the paradoxes. If wormholes exist, if black holes connect distant regions of space and time, what happens to causality? Could you travel through a black hole and arrive before you left? Could you send a message backward in time, rewriting history? The equations suggest it's possible, but the universe may have its own defenses. Some physicists think that the laws of physics conspire to prevent paradoxes, that wormholes collapse or radiation builds up to stop them from being used. It's as if the universe enforces a kind of cosmic censorship, keeping the most dangerous possibilities hidden behind the horizon. Cosmic censorship itself is an idea worth lingering on. It's the proposal that singularities must always be hidden behind horizons, never exposed to the outside universe. Naked singularities without horizons would break the predictability of physics, allowing light to escape from places where the laws no longer apply. If such things exist, the universe would lose its order. But so far, every known black hole keeps its secrets hidden. The censorship holds, at least as far as we can see, so we're left with a paradox of knowledge. Black holes may contain portals, time machines, even universes within them. But we can never know for certain, because no information escapes. They are like cosmic safes, locking away the answers to their own riddles. And yet, in their silence, they speak. In the radiation they emit, the waves they send, the stars they bend. They whisper clues about what they are. Think of that for a moment. A black hole is a region where time and space are twisted beyond recognition, where matter is crushed, where our theories fail and, yet they are common. They shape galaxies. They merge, sending ripples through space-time that we can detect. They are not rare curiosities. They are part of the fabric of the universe. And if inside them lies something more, a portal, a paradox, a passage to somewhere else, then the universe is far stranger than we ever dared imagine. But before we get lost in speculation, let's remember something grounding. Every black hole we see began as a star. Every portal, every paradox, every wormhole in the math begins with something familiar. A sphere of gas burning in the darkness, shining for billions of years, then collapsing into mystery. Black holes are the end of one story, and perhaps the beginning of another. And that beginning may not just be theoretical. Some physicists suggest that black holes could spawn new universes, that inside each singularity, space-time doesn't end, it tunnels through to a fresh expansion. A new Big Bang, a whole cosmos branching off from ours. If so, then maybe our universe was born inside someone else's black hole, an offspring of a larger reality. In that case, black holes are not just ends or beginnings. They are both gateways, seeds, paradoxes made flesh. But how do we test that? How do we know whether these wild possibilities are real, or just dreams painted in equations? The horizon hides too much. We need another way, a crack in the darkness, some hint that can reach us across the void. And in the next part of our journey, we'll explore those cracks. Hawking radiation, the holographic principle, and the information paradox. Because black holes don't just bend space and time, they bend the very rules of reality itself. For now, rest with this thought. Somewhere, perhaps right now, a traveler is falling across a horizon, carried into silence. To us, they are frozen, fading, forever suspended at the edge. To them, they are plunging inward, toward something we cannot imagine. Two realities, both true, both irreconcilable. That's the hidden life of black holes. Not just objects, but paradoxes. And the deeper we look, the stranger the story becomes. If black holes are prisons for light, then how could they possibly shine? For centuries, the answer was simple. They couldn't. They were the ultimate dead ends, swallowing everything and revealing nothing. But in the 1970s, a young physicist named Stephen Hawking turned that certainty upside down. By daring to combine quantum mechanics with black holes, he discovered something extraordinary. Black holes aren't entirely black. They glow. Faintly, invisibly to the eye, but undeniably. They radiate. It sounds impossible. After all, the very definition of a black hole is that nothing escapes it, not matter, not light, not even information. But Hawking realized that the strange rules of quantum physics don't play by those expectations. In quantum mechanics, empty space isn't really empty. It's a seething froth of particles and antiparticles popping into existence, annihilating and vanishing again in the blink of an eye. Normally, this happens everywhere with no net effect. But near a black hole's event horizon, the story changes. Imagine a particle and antiparticle pair forming just at the edge. One falls in, the other escapes. To an outside observer, it looks like the black hole has emitted a particle. But the energy has to come from somewhere, and it comes from the black hole itself. Slowly, over eons, the black hole loses mass. It evaporates. This is Hawking radiation, the faint whisper of quantum mechanics leaking from the strongest prisons in the universe. For stellar mass black holes, the effect is tiny, utterly drowned out by the surrounding glow of hot gas. But for smaller hypothetical black holes, the evaporation could be faster, even explosive at the end. And the principle holds for all. Given enough time, every black hole will fade away. Its mass returned to the cosmos as radiation. But Hawking's discovery opened a wound that physics has not healed. Because if black holes evaporate, what happens to the information inside them? Remember, in physics, information is sacred. If you burn a book, the words are gone, but the information isn't. In principle, the smoke and ash still contain every detail, scrambled but recoverable. The laws of quantum mechanics insist that information cannot be destroyed. But what about a book tossed into a black hole? The horizon seals it off. The Hawking radiation leaking out carries no trace of what fell in, and when the black hole finally evaporates, it seems the information is gone forever. That's the black hole information paradox. For decades, physicists argued. Some said information must be destroyed, that black holes mark exceptions to the rules. But this would shatter the foundations of quantum mechanics, undermining the very predictability of the universe. Others insisted the information must escape somehow, encoded in the Hawking radiation. But how? The radiation appears perfectly random, with no sign of hidden messages. And still others suggested the information remains on the horizon, stored like a cosmic archive, waiting to be released. This last idea led to one of the most profound developments in theoretical physics: the holographic principle. It began with black holes, but spread to the universe itself. The proposal is simple, but radical. The information about everything inside a black hole is not lost. It's encoded on the event horizon, in a two-dimensional surface that contains all the data of the three-dimensional interior. In other words, a black hole is a hologram, projecting its interior from its boundary. Take that idea further, and it implies something breathtaking. Perhaps the entire universe is like that. Perhaps everything we experience in 3 dimensions is a projection of information encoded on a distant boundary. We may be living in a holographic reality. Black holes, in their silence, may be the key to revealing the very nature of existence. But, back to the paradox. If information is encoded on the horizon, then Hawking radiation might, in principle, carry it away, not as random noise, but as an impossibly scrambled code. Imagine shredding a book into dust, scattering the dust across the ocean, and still being able to reconstruct the words if you had infinite patience. That's the scale of difficulty we're talking about. Yet physics demands it may be possible. The paradox forces us to think differently about what information is and where it can reside. Of course, not everyone agrees. Some physicists propose that the horizon is more violent than we thought. Instead of a smooth boundary, it could be a firewall, a region of searing energy that burns anything crossing it, releasing the information immediately. If that's true, the paradox is solved, but at a cost. It means Einstein's equivalence principle. The idea that falling across a horizon feels smooth is wrong. It means black holes are not gentle entrances but fiery walls. It's a brutal possibility, one still fiercely debated. Others push even further. Maybe information doesn't escape or burn. Maybe it leaks into new universes created inside black holes. In that case, it isn't lost, it just leaves ours. Every black hole becomes a passage, not just for matter, but for information itself, carrying stories of our universe into others we'll never see. That would preserve the laws of physics, but at the price of making them even more strange. And then there are the whispers of something deeper. That space-time itself is woven from information. That black holes aren't just puzzles about gravity, but windows into a new theory where geometry, quantum mechanics, and information are inseparably linked. Some even suggest that the fabric of the universe is a kind of quantum error-correcting code. Resilient, self-preserving, making sure information is never truly lost. If that's true, then black holes are not mistakes in the code. They are part of the code itself. Think about what that means. Black holes, once feared as destroyers, may actually be teachers. Their paradoxes are not signs of failure, but hints that the universe is built from rules we don't yet understand. They are forcing us to see reality differently, to look beyond the limits of relativity and quantum mechanics, to search for something new that unites them. It's humbling, isn't it? The darkest objects in the universe are the brightest beacons of understanding. Their silence roars with questions. Their horizons hold the secrets of time, space, and information. By staring into the abyss, we are learning what reality itself may be made of, and yet, the paradox remains unresolved. Is the horizon smooth or fiery? Is information scrambled and released, or hidden and passed into other universes? Is the radiation random noise, or a code we have not yet learned to read? These are not trivial puzzles. They cut to the foundation of physics. Our future understanding of the universe may depend on which way the answers fall. But maybe the most staggering implication of all is this. Black holes might be mirrors. Not mirrors of light, but mirrors of reality itself. They reflect back to us the deepest structure of existence, forcing us to ask, is the universe itself a hologram? Are we projections on a cosmic horizon? Shadows of information written on a surface we'll never touch. It's dizzying. It's unsettling. But it's also thrilling. Because in chasing these questions, we are not just learning about black holes. We are learning about ourselves, and our place in the cosmos. For now, let's pause here. We've walked from Hawking's quiet insight to the edge of holographic reality. From radiation to paradox to firewalls to holograms. Each step stranger than the last. And yet, each one rooted in the silence of those dark horizons scattered across the galaxy. Next time, we'll push further outward and upward. We'll leave the mathematics of the horizon and explore the role black holes play in the grand architecture of the cosmos. Because while they hide secrets in their depths, they also shape galaxies, sculpt stars, and may even be essential for life itself. Black holes aren't just mysteries in the darkness. They are engines of creation. And in Part 5, we'll see how the monsters at the centers of galaxies may hold the keys to everything we know. When you picture a black hole, It's easy to imagine them as cosmic villains, monsters lurking in the dark, devouring stars, swallowing light, erasing everything that dares wander too close. And in many ways, that picture is true. They are the ultimate consumers, the hungriest objects in the universe. But here's the twist. Black holes are not just destroyers. They are builders. They are sculptors of galaxies, engines of creation, perhaps even essential to the existence of life itself. To see this, we need to step back from the abyss and look at the bigger picture. Look at galaxies, those sprawling cities of stars, spiral galaxies like our Milky Way, elegant pinwheels of light stretching across hundreds of thousands of light-years, elliptical galaxies, giant glowing orbs, irregular galaxies, chaotic and scattered, different shapes, different histories, but all with something in common. At the heart of nearly every large galaxy lies a supermassive black hole, millions, sometimes billions, of times the mass of the Sun. Invisible, but undeniable, our own Milky Way's central giant, Sagittarius A*, is relatively modest by galactic standards just for million solar masses, but others dwarf it. The black hole in the galaxy M87 weighs 6.5 billion suns. Its gravity so immense it bends light into the iconic glowing ring we photographed in 2019. Some young galaxies powered by ravenous black holes shine brighter than entire galaxies of stars, fueled by matter spiraling into their cores. These monsters are not passive, they are active players in galactic evolution. How do they shape galaxies? The answer lies in energy. When matter falls toward a black hole, it doesn't always plunge straight in. It swirls, forming an accretion disk. Friction in the disk heats it to astonishing temperatures, causing it to blaze with radiation. Some of that energy escapes in the form of colossal jet streams of particles and radiation blasting outward at nearly the speed of light. Stretching across thousands or even millions of light, these jets can outshine galaxies, sculpting their surroundings, regulating star formation, and spreading heavy elements across space. Think about that. A black hole, which swallows everything that falls in, also gives back. It spews energy into the universe, influencing the birth of stars and planets. Without these feedback effects, galaxies might collapse into uncontrolled starbursts or fizzle out altogether. Black holes, paradoxically, help maintain balance. They are both the heart and the governor of galaxies, regulating their growth. And the story goes even deeper. The relationship between galaxies and their central black holes seems to be intimate, even symbiotic. The mass of a galaxy's central black hole correlates closely with the velocity of stars in its bulge. Somehow, the black hole and the galaxy grow together, as if locked in a cosmic dance. Did the galaxy form first, with its stars gathering and later feeding the black hole? Or did the black hole form early, seeding the galaxy around it? We don't yet know, but the connection is undeniable. Galaxies and their black holes are partners in creation. On even larger scales, black holes shape the cosmos through collisions. When galaxies merge, so do their central black holes. These titanic mergers send out gravitational waves ripples in spacetime that carry energy across the universe. The waves we've already detected, from smaller black holes, are just whispers compared to the roars of supermassive ones colliding. Those, one day, may be detectable by new observatories, and when they merge, they reshape their galaxies, stirring stars, redistributing matter, sparking new rounds of star formation. Black holes, silent and dark, leave fingerprints on the universe itself. And what about us? Could it be that without black holes, life itself would not exist? The thought sounds absurd, but consider this. The heavy elements we are made of: carbon, oxygen, iron. The stuff of blood and bones and breaths were forged in the cores of stars and spread into space by supernova. But the distribution of those elements, the conditions that allowed planets to form and life to emerge, may have been shaped by the activity of black holes. Their jets, their winds, their regulation of galactic growth, or may have created the balance of environments needed for complex Panisk's chemistry to arise. There's also another possibility, more speculative but intriguing. Some scientists wonder if supermassive black holes could play a role in the very fabric of cosmic structure. Early in the universe, When matter was hot and dense, black holes may have formed quickly, anchoring the first galaxies. If so, then the great web of cosmic structure, the filaments of galaxies stretching across the universe, may have been seeded by black holes. Without them, the universe might look utterly different, perhaps empty, or chaotic, or sterile. It's a strange twist, isn't it? The things we once thought of as cosmic monsters may, in fact, be midwives of creation. Without them, galaxies might never have formed, stars might never have clustered, and planets might never have coalesced. Without them, we might not be here to ask these questions at all. But let's not romanticize them too much. Black holes remain dangerous. A star that drifts too close can be torn apart in a tidal disruption event. Its gas stretched and shredded into glowing streams spiraling into the abyss. Planets wandering near would be stripped and consumed. Even entire clusters of stars can be destabilized by their pull. Black holes give, but they also take. Their power is creative and destructive, balanced in ways we're only beginning to understand. What's most remarkable is that all of this, the jets, the galaxies, the cosmic balance, emerges from something so simple, a region of spacetime where gravity is so strong that nothing escapes. From that simplicity arises a cascade of complexity. It's as if the universe is telling us that endings and beginnings are not opposites, but parts of the same story. The death of a star births a black hole. The hunger of a black hole sculpts a galaxy. The silence of a black hole speaks in gravitational waves. The void gives rise to creation. So the next time you look up at the night sky, consider this. The Milky Way's graceful spiral is shaped, in part, by the invisible grip of Sagittarius A*. The quiet star you see may have been nudged into place by the influence of a black hole, and the atoms in your body may have been scattered into space by processes black holes helped regulate billions of years ago. We are, in a sense, children of black holes. But the story doesn't end with galaxies and stars. Black holes also play tricks with time itself. Their extreme gravity slows clocks, stretches moments, and teases the possibility of journeys into the future. In fact, black holes may be the ultimate laboratories for testing our ideas of time, and that's where we're headed next. Because if black holes are architects of galaxies, they are also architects of time. In Part 6, we'll step into the strange relationship between black holes and time travel. We'll see how horizons bend time, how falling into a black hole may feel like stepping into forever, and how these monsters may hold the closest thing to a time machine the universe has ever given us. For now, let the thought linger. The same abyss that swallows light also shapes galaxies, stars, and maybe even life. Black holes are not just hidden places in space. They are hidden threads in the fabric of everything. Time is slippery around a black hole. It doesn't behave the way we expect. Out here, on Earth, we trust our clocks. Seconds tick evenly, minutes add up to hours, and the rhythm feels universal. But Einstein showed us long ago that time isn't absolute. It bends and stretches depending on gravity and motion. And nowhere is that more extreme than near a black hole. Imagine you're watching a spaceship drift toward the event horizon of a black hole. From your perspective, far away, the ship slows as it approaches the edge. Its signals stretch into longer and longer wavelengths. The beeps of its transmissions grow farther apart, deeper, fainter, until finally, they stop. The ship seems frozen at the horizon, suspended forever, fading into the black. That's what time looks like near a black hole, from the outside. But now, imagine being on the ship. You don't feel frozen. Your watch ticks, as usual. Your heart keeps its rhythm. Time for you feels normal. You cross the horizon without noticing anything special. But, if you could look back at Earth, you'd see time racing. Hours, days, years, centuries flashing by. Civilizations rising and falling in the blink of your eye. For you, time has slowed compared to the universe outside. This is time dilation, the stretching of time caused by intense gravity. In a sense, black holes are natural time machines, but only into the future. Spend an hour orbiting near the event horizon, and when you return to distant space, you might find that centuries have passed. The closer you get to the horizon, the more dramatic the effect. And if you could hover just above it, impossible in practice. But imagine you could watch the universe age while barely a moment passes for you. Black holes let you leap forward in time simply by waiting in the right place. This isn't just science fiction. Time dilation has been confirmed in experiments on Earth. Atomic clocks flown on airplanes tick at slightly different rates than those left on the ground. Satellites orbiting Earth experience time at a different pace than we do here. GPS systems have to account for relativity, or they'd quickly drift out of sync. The effect is small in Earth's gravity, but near a black hole, it becomes overwhelming. The laws are the same. The stage is just more extreme, but what about traveling to the past? That's where the paradoxes begin. Some solutions to Einstein's equations suggest that rotating black holes might contain pathways that loop back in time, closed time-like curves hidden within their warped geometry. If such paths exist, then black holes could be gateways, not just to other places, but to other times. But the math is fragile, unstable. The tiniest disturbance collapses the loop. And even if they did exist, the paradoxes of time travel grandfathers. Bootstrap loops, causality violations might forbid them. It's as though the universe allows us glimpses of the past in the equations, but slams the door when we try to walk through. Still, the possibility lingers. Could a black hole be a portal to yesterday? Or to tomorrow in another branch of reality? We don't know. Some physicists argue that nature has a kind of built-in censorship, preventing time travel to the past, protecting causality at all costs. Others suspect that the multiverse may absorb the paradox's every change, spawning a new branch. Every contradiction resolved by splitting reality. If so, then perhaps falling through a black hole doesn't trap you in a loop, but pushes you into another version of the universe. One where the past you alter isn't the same past you left. Speculation aside, one truth remains. Black holes reveal time itself as flexible. They show us that the flow of moments is not universal, but relative. That what feels like an hour for you may be centuries for me. That the fabric of time is not rigid, but curved, stretched, twisted by gravity. To study black holes is to study time travel by another name. And this leads us to an unsettling thought. If black holes can slow time to such extremes, then what happens at the singularity? If space collapses, does time collapse too? Does it stop altogether? Or does it flow into some other direction, inaccessible to us? Could the singularity be a place where our concept of time simply ceases to exist? These are not just academic puzzles, they touch the deepest mysteries of reality. There's a haunting idea hidden here. Imagine an astronaut falling into a black hole. To us, they never cross the horizon. They're frozen, fading, unreachable. But to them, they plunge inward, swiftly, At the singularity, their timeline ends. To us, it's as though they are trapped forever at the edge, never quite gone. To them, they are erased in moments. Both stories are true, but they can't be reconciled. Two perspectives, two realities, each valid, each incomplete. Time itself fractures at the horizon dot, and yet, even in these fractures, black holes may hold the key. If we can understand how time behaves at their edges, maybe we can learn how time itself is woven into the universe. Maybe black holes are not just natural laboratories for gravity, but for time, the closest thing to a time machine the universe has to offer. For now, we can only watch from afar, measuring the orbits of stars, listening to the ripples of space-time, gazing at the glowing rings around their shadows. But in those observations, we are already testing time. Every photon bent, every wave rippling, every clock slowed in gravity's grip is a message from the edge of the abyss. A message about what time really is. Next time, we'll follow that message further. Because if black holes test our understanding of time, they also test our understanding of destiny. In Part 7, we'll explore free will, determinism, and the choices we make in a universe shaped by these monsters. If black holes bend time, then what does that mean for us, the tiny beings carried along its current? Are we free to choose, or are we bound to paths already written? For now, let this thought settle. Black holes are more than darkness. They are clocks, distorted and strange, ticking at rhythms we can barely comprehend. And if you linger too close, they may carry you into a future you can never return from. Black holes don't just bend light and matter. They bend the way we think about time itself. And once you start thinking about time, the next question follows close behind. If time is curved, if moments can stretch or vanish, if the future is already written in the fabric of space-time, then what does that mean for us? Do we really make choices? Or are we like stars orbiting Sagittarius A*, locked into paths carved long before we were born? It's a question older than black holes, older than physics. Philosophers have wrestled with it for centuries, but black holes sharpen the question into something unavoidable. When you look at the event horizon, when you watch the paradox of time dilation unfold, you can't help but wonder, are we free, or are we passengers? Einstein himself leaned toward determinism. In his view, the universe is a four-dimensional block of space-time. Past, present, and future are all equally real, already existing. We don't move through time so much as we experience it slice by slice. In that picture, free will is an illusion. Our choices are just points on the timeline, already laid out, waiting for us to notice them. But living that way feels strange. We feel the weight of choice. We feel the uncertainty of not knowing what tomorrow will bring. Black holes amplify the tension. If falling into one slows your time so that the outside world races ahead, then from your perspective, you're choosing to step into the unknown. But from the outside, maybe your fate was already sealed, frozen on the edge of the horizon, playing out in slow motion. Both views are true. Both are contradictory. And both make free will feel slippery. Now consider the information paradox again. If nothing is ever truly lost, if information is preserved, then maybe every detail of your life is encoded in the fabric of the universe, forever. Every decision, every heartbeat, every thought. That could mean you were never really free. Your choices were always bound into the cosmic script. On the other hand, if black holes allow information to escape scrambled, or pass into new universes, then maybe choice is real. Scattered across branches of possibility. Maybe every decision you make sends echoes into countless outcomes. Like light bent into many paths by gravity. It's unsettling. In one version, we are puppets of space-time, our strings pulled by equations written at the beginning of the cosmos. In another, we are fractal beings, endlessly branching across realities. In both, the feeling of free will may be nothing more than a side effect of time's flow. And yet, that feeling is undeniable. You chose to press play on this story. You choose whether to keep listening. The sense of agency is too strong to dismiss. Maybe free will is emergent, not fundamental, but real enough to matter like the warmth of fire, born from molecules moving, but experienced as something greater than the parts. Black holes force us to sit with the discomfort. They remind us that two perspectives can be true at once. From outside the horizon, nothing crosses. From inside, everything does. From one view, you are frozen. From another, you are falling. Maybe free will and determinism are like that, two descriptions of the same reality. Both valid, both incomplete. There's a haunting thought experiment that drives this home. Imagine you hover near a black hole, watching the universe race into the future. You could, in principle, wait until the heat death of the cosmos, all while living through only a few hours yourself. To you, it feels like you've chosen to jump ahead. But in the grand scheme, that leap was always encoded in the space-time fabric. Did you choose? Or did the timeline dictate? We find ourselves circling the same paradox. Perhaps free will exists in the same way time exists. Emergent, local, subjective. For the astronaut falling inward, there's still choice, still action, still the rhythm of life. For the outside observer, the story is already written. Which is true? Maybe both. Maybe our lives are like black holes, mysteries seen one way from inside, another way from outside, never fully reconciled. And maybe that's the real lesson. Black holes aren't just cosmic objects. They're metaphors for our lives, boundaries of knowledge, mirrors of paradox, teachers of humility. They show us that the universe is not obligated to resolve our contradictions. Sometimes, reality contains both sides of the story. So what do we do with that? Do we surrender to determinism? Accept that our futures are carved into the stars? Or do we embrace the lived experience of freedom, however illusory, and act as if our choices matter? Maybe the answer isn't one or the other. Maybe it's both. Maybe the paradox is the point, because whether or not free will is real in the deepest sense, the experience of it shapes us. The act of choosing what to love, what to create, what to value defines who we are. And if black holes teach us anything, it's that sometimes the experience is as real as the underlying physics. A horizon is not a surface, but it feels like one. Free will may not be fundamental, but it feels like it is, and that may be enough. So here we are, staring at the abyss, not just of space, but of meaning. Are we free travelers, or passengers locked on rails? Are black holes portals of possibility, or prisons of inevitability? The truth may never come neatly wrapped, but the asking of the question, that's the journey. That's the real-time travel dot, and it brings us to the endgame. Because if black holes push us to confront paradoxes of free will, they also push us to confront endings. They evaporate. They merge. They shape the fate of galaxies, and maybe even the fate of the universe itself. In Part 8, our final chapter, we'll step into that last horizon. We'll ask what black holes mean, not just for physics, but for us, for the story of the cosmos, for the story of time, for the story of everything, for now. Rest with this thought. Somewhere, at the center of our galaxy, Sagittarius A** spins in silence. Around it, stars whirl in precise orbits, dancing to a rhythm written long ago. Are they choosing their paths, or are they bound to them? Look up at the night sky, and you are looking at that dance, at that paradox. Maybe you are part of it too. We've walked a long road together, from the birth of black holes in the deaths of stars, to the mysteries of their horizons, to the paradoxes of information and time. We've seen them not just as destroyers, but as sculptors of galaxies, as laboratories for physics, as mirrors for questions of free will and fate. And now, we've arrived at the final horizon, because black holes don't last forever. They live, they change, and in the end, they die. Their story, like every story, has an ending. And in that ending lies one last set of mysteries. Picture a stellar mass black hole, the corpse of a massive star. For eons, it waits, silent, invisible, perhaps feeding now and then on stray gas or a passing star. But even if left alone, it is not eternal. Hawking showed us that black holes evaporate. Slowly, unbearably slowly, they leak radiation. For a black hole with the mass of the Sun, the evaporation time is years vastly longer than the current age of the universe. For supermassive black holes, the timescale is even greater, 10,100 years or more. To us, they seem eternal. But time is patient, and in the far future, long after the last stars have burned out, after galaxies have faded into darkness, black holes will remain as the last actors on the cosmic stage. In that deep future, the universe will be quiet. No new stars will be born. The cosmos will be a cold, dark expanse sprinkled with black holes, slowly evaporating. One by one, they will fade, shrinking smaller, hotter, brighter, in their last instants. In their final moments, they will release bursts of energy, the last fireworks of the universe, until nothing remains. The night sky will go dark. The story of black holes will end in silence. And perhaps, so will the story of the universe. But before that far future, black holes have another role to play: collisions. We've already detected their gravitational waves, ripples in spacetime from black holes spiraling together. Each collision sends a shudder through the universe, a vibration we can now listen to with instruments like LIGO and Virgo. In the future, we may hear the roars of supermassive black holes colliding when galaxies merge. These events reshape the cosmos, leaving behind bigger black holes echoing across spacetime itself. In some sense, every black hole is both a grave and a womb, ending one story, beginning another. And then there are the larger questions. What role do black holes play in the fate of everything? Could they trigger the birth of new universes? Could their evaporation seed the vacuum with strange particles? Could the end of a black hole mark the beginning of something else? Some scientists think so. If every black hole spawns a new cosmos inside, then black holes may be the link in an infinite chain of universes, each born from the death of another. In that vision, black holes aren't endings at all. They are doorways, branching paths in an eternal multiverse. Even if that's speculation, one thing is certain: black holes have already changed our understanding of reality. They've forced us to rethink gravity, time, information, and the very fabric of space. They've shown us that the universe is stranger than we imagined, and perhaps stranger than we can imagine. They are boundaries in knowledge, edges where our theories collapse and our imaginations strain. They remind us that we don't have all the answers, sand maybe never will. But perhaps that's the gift of black holes. Not answers, but questions. Not certainty, but mystery. They are reminders that the universe is vast, humbling, and still full of wonder. That even in the darkness, there is beauty. That even in the silence, there is meaning. Black holes are terrifying, yes, but they are also sublime. They are nature at its most extreme, and in studying them, we glimpse the edges of what it means to exist. So what do they mean for us? On one level, they are distant curiosities, millions of light years away, irrelevant to our daily lives. But on another level, they are part of our story. The atoms in our bodies, forged in stars, scattered by supernova, may have been stirred and distributed by the influence of black holes. Our galaxy's shape, the stars we see, the planets we walk on, these may all be part of their legacy. Without black holes, we might not be here at all. And beyond that, they mean something deeper. They mean that the universe is not simple. That the more we learn, the more questions emerge. That reality is not a flat, predictable thing, but a labyrinth of paradoxes and possibilities. Black holes are nature's way of reminding us that we live in a cosmos too grand to be reduced to easy answers. And that's not frightening, it's exhilarating. So as we close this journey, let's pause and reflect. Somewhere out there, right now, stars are orbiting invisible companions, their light curving around the darkness. Somewhere, gas is spiraling into a horizon, glowing as it falls. Somewhere, two black holes are circling closer, about to collide and send ripples across space-time. Somewhere, in the far future, a black hole is evaporating, its last photons whispering into the cold night. And here we are, tiny creatures on a small planet, thinking about it all. That's the real wonder. That we can look up at the night sky and imagine the invisible, the unreachable, the unknowable. That we can take equations and telescopes and minds full of curiosity and stretch them across the universe. That we can fall into the mystery without ever leaving home. Black holes are not just cosmic objects. They are symbols of our hunger to know, our willingness to face the unknown, our courage to ask impossible questions. They are reminders that even in the darkest places, there is something to see, something to learn, something to wonder at. So here, at the end of this long journey, let me leave you with this. Black holes are not the end. Not for stars, not for galaxies, not for us. They are thresholds. They are horizons. They are mysteries waiting at the edge of time. And by looking into them, we are not staring into oblivion. We are staring into possibility. Thank you for traveling with me, through the darkness, through the paradoxes, through the hidden life of black holes. Wherever you are, whenever you are, remember this: you are a traveler too. Every second, every breath, you move through the fabric of space-time. You don't need to fall into a black hole to be part of the mystery. You already are, and maybe, in some far-off future, when the last black hole evaporates into silence, the echoes of our questions will still be there, written into the fabric of the universe, carried by the very radiation of the abyss, proof that even in the face of the unknown, we dared to wonder.